So, section 7.6 and 7.7 is going to show how to solve a system of equations by using matrices. So if we have a system of equations where we have, let me write it down here first. If we have it set up where we have all the x values lined up, all the y values lined up, and all the constants lined up over there on the other side of the equal sign, then the most important information we really care about is just those coefficients. And so we have something called an augmented matrix. Augmented matrix pulls out just the most important information, which we said is those coefficients. And then from there, we can solve the system using something called row operations. So first, we need to get comfortable with taking a system and put it into an augmented matrix. Once we do that, we have just the most important information. Now let's talk about row operations. What can we do with a system? A matrix. Okay, there's a lot of different things you can do with matrices. Right now, we're just going to talk about row operations because we're going to use row operations to solve or to put these matrices in a certain form, which will eventually solve the system. So the first row operation we can do is we can switch any two rows. We can just take two rows in a matrix and just switch them. We can multiply a row by any non-zero real number. Okay? And then the last thing we can do is we can add, let me do this. Let's say we can replace a row by it and the sum. I don't like what I'm saying here. Let me say this. Let's do this. Let's say we can add any row to another row. That's probably a better way to word it. Okay, so if we use those three row operations, we want to take the system and put it in something called row reduced echelon form. Row reduced echelon form for a matrix that has two rows and three columns looks like this. Okay? Because basically what this says, if we convert it back to a system, is 1x plus 0y equals some number, and 0x plus 1y equals some number. Well, we don't have to really write out all that. We can basically just look at it and say x equals a and y equals b. For a bigger one, three variable, when we convert it over, it looks like this. This says x equal to a, y equal to b, and z equal to c. Okay, so if we can get it to row reduced form using our row operations, we can pull the solution out fairly quickly. Okay, so let's do an example. Let's say I have the system 3x minus 4y equal to 1 and 5x plus 2y is equal to 19. If we put it into a matrix, that's 3, negative 4, 1, 5, 2, 19. Okay, so just like with elimination with a system, we want to get rid of this guy. We want that to be a 0. So we're going to do it basically the same method, But I'm going to make the notation just a little different here. Okay, so I'm going to take 3 times row 2, and I'm going to subtract 5 times row 1. I make that note to myself, and I put it beside row 2 because that's the row I'm replacing. I'm going to take those two and put them together. So the top row I'm not changing, I'm just using it. It's the second row I'm changing. So here, follow my steps that I have notated out to the side. 3 times row 2 minus 5 times row 1, that's 15 minus 15, which is 0. Then I have 6 minus a negative 20, so that's plus 20, so that's 26. Then we have 57 minus 5, which is 52. Okay? Now, if I look back at my row reduced echelon form, I need a 1 in this position. And if I go back and look, I have a 26 in that position. I need it to be a 1. So how do I get 26 to be 1? Well, I divide it by 26, or the same thing as multiplying by 1 over 26. And that gives me the top row stays the same, bottom row becomes 0, 1, 2. Okay? Now I need this guy to be 0. This guy right here. So I'm going to use the bottom row. So I can take row 1 and add 4 times row 2, and that should eliminate that guy. So if I come up here to the top, 3 plus 0 is still 3. Negative 4 plus 4 is 0. Then I have 1 plus 8, which is 9. And the bottom row stays the same. And then my very last step for row reduced echelon form is I need a 1 in that position there. And I have a 3. So I'm going to divide everything in row 1 by 3, which gives me 1, 0, 3, 0, 1, 2. So straight from there, we can see that the solution is x equal to 3, y equal to 2. Now, this is more steps than doing elimination with the systems, but it's cleaner. You know, we cut out all the extra stuff. We have a new notation that makes us actually help us skip steps without having to show us multiplying all those rows. We can just do it as we go. So whenever we go to a 3 variable system, it actually cuts down how much work excuse me, how much work we have to do. So let's do another example. Let's say I have 4x minus 2y equals 23, negative 5x minus 10y equals negative 35. So if I convert it to a matrix, that's 4, negative 2, 23, negative 5, negative 10, negative 35. Now, before I proceed much further, I want you to look at that bottom row. Everything is divisible by a negative 5. So I can simplify that row by going ahead and multiplying by negative 1/5. Top row stays the same, and then that row becomes 1, 2, and 7. Okay? Now, in row reduced echelon form, let's go back to that page. You see I have a 1 in this first position here. But I have a 1 on the second row. So if I want to put that 1 in that position, I can just switch the 2 rows. That's one of my row operations. And that would take care of having a 1 in that first position. You don't have to do that, but if it's there, we have that option. And then now if I want to eliminate that 4, I can do row 2 minus 4 times row 1. So then that becomes 0. And then negative 2 minus 8 is negative 10. And then we have 23 minus a 28, which would be negative 5. Now, I can divide by that negative 10 right now, but it's going to give me fractions, and we don't want to deal with fractions until we get to the very end. But I can simplify that second row. So let's go ahead and simplify that second row by dividing by 5. Oops, that's row 2. So up here we would have 1, 2, 7, and 0, negative 2, negative 1. Then you can see that the negative 2 and the 2 already line up. So if I want to make that 2 in the top row 0, I just need to add those. Let me give myself a little bit more room here. So then I can do row 1 plus row 2 to get rid of that 2. Because if I take the 1 and add 0 to it, it still is 1. Then that goes 0, and then we have 6. And the bottom row is 1, or 0, negative 2, negative 1. And if I want to make that guy a 1, that negative 2, 1, I'll just divide by, or multiply by negative 2. And we get 1, 0, 6, 0, 1, 1 half. So the solution is x equal to 6, y equal to 1 half. Okay? Last example we're going to do here. Say I have x plus y equals 2. 2x plus 2y is equal to 5. If I put it in a matrix, I get 1, 1, 2, and 2, 2, 5. Now, right here, I want a 0 in that position. So if I take row 2, to do that, let's say I take row 2, and I subtract 2 times row 1, top row stays the same, second row becomes 0, 0, and then we have 5 minus 4, which is 1. Now we have to stop right there because that bottom row says 0x plus 0y equals 1, which essentially is 0 equals 1, which is an untrue statement. And if you refer back when we were talking about having an untrue statement, whenever we add two equations in a system together, this is essentially the same thing. And so we say this is inconsistent and there's no solution. Okay, so we'll stop there.